Ok, adesso stiamo registrando. Facciamo lo sharing. Ok, mi confermate che mi sentite e che vedete il mio schermo?
Sì, prof.
Sì.
Benissimo. Ok, allora, let's start. So, at the end of the last lesson, we derived the full expression of the Lagrangian density of QED, of quantum electrodynamics, which is, as you now understand, the quantum field theory of the electromagnetic interaction. And you find it here. So we have a first term, which includes the kinetic and the mass term for the fermion, for instance, an electron or a positron or whatever. Then we have an interaction term, okay, where now the fermion field interacts with this vector boson field, our gauge boson. And then we have a last term, which is the kinetic term for the gauge boson itself. And if you remember, we don't have here any explicit mass term for the boson, because if you put by hand the mass term here for the photon or for whatever boson you want to put here, you will immediately break the gauge invariance of the Lagrangian, okay? And this is consistent with the fact that indeed the photon is a massless boson. We will see now how things are completely different for the case of the weak interaction, of course, where the gauge bosons, the W and the Z are massive, actually very massive. Okay, now, how did we recover or derive these Lagrangian? So let me summarize the main steps. So we started from the Lagrangian density for a free Dirac fermion, okay, here. Then we required for this Lagrangian density to be symmetric under local U1 phase transformation of this type, where local means that the parameter of the transformation depends explicitly on the space-time coordinates. Then we find out that with this, under this transformation, the Lagrangian is not symmetric, so we need to make a trick. So we need essentially to substitute our standard derivative with the covariant derivative, which now includes a new object, which is indeed our gauge boson, which must be transformed in the proper way in order to recover the symmetry of the Lagrangian density under this local transformation. And so you need here to have a term with the derivative of the parameter in order to cancel the same term that arises when you simply apply your transformation to the standard Lagrangian density. And the last term is given in terms of the electromagnetic strength tensor, F mu nu, which you can even write also in terms of the photon field, okay, in this way. Now, the Feynman approach to QED is rather different, and this is what we will study today, and is based on perturbation methods applied to the single particle wave function. And in particular, Feynman developed, as you know, the rules for evaluating the transition matrix elements for the various electromagnetic processes and for representing them graphically through spatial diagrams, the famous Feynman diagrams that we will study today. So Feynman diagrams are not only useful pictorial representation of the various processes, but they represent specific mathematical expressions. Okay. In particular, each diagram corresponds to a specific term of a perturbative expansion of the scattering amplitude, and each symbol in the diagram corresponds to a specific term in the transition matrix element. Okay. And the correspondence is encoded in the so-called Feynman rules for QED that we will be studying today. Okay, and similar rules have been developed also for the strong interaction and the weak interactions. So there are 6 basic Qed vertices, okay, and these are the only one possible, essentially, at least for the electron sector. Then we have, of course, the same for the quark sector and for the other leptons. So we have the first process is the emission of a photon by an electron, okay? So in the initial state, we have an electron. In the final state, we have an electron plus the emitted photon. Or we have the absorption of a photon by an electron. Then we have the same processes, but now for positrons, so for the antiparticle. And then we have the annihilation process, where an E plus E minus particle annihilate into a photon, or the pair production, where a photon produces an electron-positron pair. So these are, let's say, the basic QED vertices, but this does not mean that these diagrams correspond to real process. And in fact, as we studied already 2 lessons ago, This cannot be a real process because energy conservation is violated if all three particles are real. Okay. So in order to describe real processes, we need full diagrams like this, okay, where now we have at least two vertices in each one, and where the process is interpreted as the exchange of a virtual particle in between. Okay. So the first example here is the electron-electron scattering, which is also known as the Molar Scattering. And today we will study this process in quite some detail. Another process is the Baba scattering, which is now the electron-positron scattering, always mediated by the exchange of a virtual photon. Then we might have more complex QED processes. For instance, the Bremsstrahlung. Bremsstrahlung, as you know, is the emission of a real photon by an electron in the Coulomb field of a nucleon, for instance. In this case, you have three vertices, as you see here. And similarly, the pair production, so the real process of pair production, we have a photon that provides a pair of electron and positron, but again, in the Coulomb field of a nucleus. And this you need in order to ensure momentum conservation and energy conservation, which you cannot have in these basic vertices here. So let's now start studying the approach of Feynman, which is based indeed on perturbation theory. And then we will see the correspondence between the matrix element that we studied in the previous lessons and the Feynman diagrams. So let me start from the very beginning. So if you remember, we derived the non-relativistic transition amplitude at first order and in Born approximation. So this is the general expression for the transition matrix element at first order. Then, if you remember, we substitute here the Yukawa potential. Okay, in general, this potential energy you can write as a coupling constant plus times potential. And when we put here the expression of the Yukawa potential, we end up, if you remember, with this kind of object, where in the numerator we have the product of the two coupling constants, and the rest is the bosonic propagator. Okay, where Q is the transverse momentum, Pi minus Pf. So this we derived formally for the non-relativistic case. Of course, now we want to discuss relativistic processes. So we need to translate these into a Lorentz invariant language. Okay, we will not do the passages, we will not do the algebra, but essentially the procedure is the same. And at the end, you will end up with this kind of transition matrix element. Okay, where now psi I, psi f are spinor, so they are solution of the Dirac equation, and of course the integral is in the four-dimensional space-time coordinates. Now, following an analogous derivation based on perturbation theory, so following, let's say, a derivation analogous to the non-relativistic one that we did, okay, one obtained the following expression for the boson propagator, okay, which is, if you compare this, is rather different, of course, than the classical one, the non-relativistic one. So here, first of all, Q square is the square, the 4 momentum, okay, this is the square, the 3 momentum instead. For momentum, that corresponds to the T-Mandelstam variable, which is the 4 momentum transfer indeed. So you can write as P1 minus P3 squared or P2 minus P4 squared. Okay, and this is the T-Mandelstam variable, if you remember. But we'll see then, okay, other cases later on. But what about the numerator? In the numerator, we have this object here, okay, which denotes the sum over all possible spin states of the exchanged boson. So in this case, of the exchanged photon. So let's now see what are the possible spin state of a photon, okay? So in general, a free photon field, a mu, free means in the absence of charges around, can be written in terms of a plane wave, okay, and a polarization vector, epsilon lambda, that describes the polarization state of the photon. Now, real photons can only have 2 independent polarization states. So suppose that the photon propagates along the z direction, the 2 polarization states are along the 2 transverse directions, so along x and along y, okay? And so you can write down this polarization state in this trivial way, okay? Where the last is z, so this is x and this is y. These are 4 vectors, okay? Now, you can also combine them, okay? So if you take this combination of epsilon1 and epsilon2, or this other combination with the minus sign between epsilon1 and epsilon2, you end up with the so-called right and left circular polarization vectors for the photon. And this describes a photon of helicity +1 and -1. Now, this was for real photons. Let's now see what happened for virtual photons, okay? So a virtual photon has instead 4 polarization states, the 2 transverse, so the same as the real photons, but in addition, also 1 longitudinal polarization state, so along the direction of motion, okay, and 1 scalar, so means spin equals 0. So in total, there are 4 for a virtual photon. And it can be shown, this we will not do here, okay, it's quite complicated, but it can be shown that the sum over all the polarization state of the virtual photon corresponds to the metric tensor that we introduced already in the very first lesson, okay? The metric tensor of special relativity, this one here. And so we can now write down the photon propagator in a more compact way, okay? Just by substituting -g mu nu instead of this sum over the polarization state, and of course, by considering that the mass of the photon is 0, okay? So what you see here, -I g mu nu divided by q square is indeed the propagator for virtual photon exchanged in all QED processes. Now, let's consider a process like this, okay? So here the process is an E plus E minus annihilation that goes into a virtual photon that provides in the final state a generic fermion-antifermion pair, okay? Now, the 4 momentum of the photon, we can always write as usual as a 4 vector. So we have the time-like component and the 3 space-like components. And for this kind of processes, okay, it is given by the sum P1 plus P2, so the sum of the initial 4 momenta, and by 4 momentum conservation, of course, this must be equal to the sum of the final state 4 momenta. So P1 plus P2, or equally P3 plus P4. Now, if you remember, if you take the square of this sum, this is exactly the S Mandelstam variable, okay? So we can now substitute in our propagator for this kind of processes, instead of q square, which can just put here the S Mandelstam variable. And this is the reason why this kind of diagrams are also called S channels, because the S, because you can express your transverse for momentum squared in terms of the Mandelstam S variable. Now, since the Mandelstam variable are Lorentz invariant by definition, by construction, they can be evaluated in any frame. So, for instance, in the center of mass frame, where you have the P1 and P2 for momenta, which must be opposite, where the 3 momenta must be opposite, okay, it turns out that this term here goes to 0 when you evaluate q square, and so you just have the square of the energy, which is always positive. So, to summarize this, we can say that the q square is always positive for S-channel processes, like this one here. And this means that if you remember back our first lesson in relativity, this means that the square of the time-like component of Q is always larger than the sum of the squares of the 3 space-like components. Okay, so overall, the result is positive when you take the square. And for these reasons, the exchanged virtual particle is named time-like. So in this case, we say that a time-like photon is exchanged. Okay, so S-channel implies a time-like photon and a q square equal to the S Mandelstam variable. However, we can also have diagrams like this one, okay, which looks like 90 degrees rotated with respect to the previous one, okay? Again, we can write in general our q, so the 4 momentum of the extended photon in terms of the time-like component and the space-like component, but in this case, the q is given by the difference between the initial and final state 3 momenta. So either 4 momenta, sorry, either plus P1 minus P3 or P2 minus P4. And if you remember, if you take the square of this corresponds to the T Mandelstam variable. And so you can substitute T into the bosonic propagator for this kind of processes. And for these reasons, these kind of processes are called T-channel. Okay? because we have T here in the propagator. And then one can make again the same exercise, and it turns out that the Q square is always negative for T-channel processes, so opposite to the S-channel case. So in this case, the square of the time-lag component of Q is always smaller than the sum of the squares of the three space-like components. And the extended virtual photon name is called space-like. So we say that in this case, a space-like photon is exchanged, which corresponds to a negative Q square and a T-Mandelstam variable in the propagator. Okay, is all clear?
Professor, excuse me.
Yes.
It is not clear to me, but maybe I don't remember why we have to make the difference between P1 and P3. Why is there a difference, for instance?
This is to ensure momentum conservation of the vertex.
Okay.
This is the only way. Okay. In this case, you ensure this. Okay.
Thank you.
So, sorry, but in that case, why is the propagator taking why is Q P1 minus P3? That's the term in the propagator itself. Myself, I don't understand. Sorry.
I don't get your question.
Yeah, I see that you have the P1 minus P3 for the conservation, but why is it that term that you use for the propagator?
So the propagator, okay, I don't know if I understand your question, but the propagator in general for the photon is given this way. Okay, this is general, always true. Now it depends whether your process is an S channel or a T channel, and in the case you can substitute here either the S Mandelstam variable or the T Mandelstam variable, because to ensure momentum conservation at the vertex, in one case your form momentum of the exchanged photon is the sum of the initial state momenta. In the other case is the difference, and in this case corresponds to the transferred form momentum from initial to final state.
Because we only look at the photon. Okay, sorry. Yes.
Okay, so it's always the form momentum of your photon, but in the two cases it's different. In one case, the sum of P1 and P2, the initial state for momenta. In the other case, is the difference between initial and final state. So this is the transverse momentum, which is indeed encoded in the T Mandelstam variable. I hope I replied to you.
Yes, that's exactly that. Thank you.
Okay, fine. Okay, having said all that, let's now go into some detail, and let me try to derive the matrix element. Okay, and so at the end of the cross-section, for the molar scattering, E minus E minus into E minus E minus, but not using the Famine diagrams for the moment, but from first principles. And then we will repeat the same calculation, but using the Famine rules, and we'll see how it becomes much easier. Okay, but it is very instructive to start from very first principles. So let me start indeed from the Dirac equation for the free fermion field psi. Okay. And we know that the solution for the free Dirac fermion is essentially a plane wave where U is our one or our solution for the spinor, okay, for the Dirac equation. Now, in this case, we are actually concerned with an electron in an electromagnetic field, okay? So the Dirac equation gets an extra term here, which ensures the interaction between the fermion field and the electromagnetic field, okay? All the rest is the same. Okay. So this is the Dirac equation for an electron in an electromagnetic field where among nu you can interpret it as a four potential, so with a scalar potential and a vector potential. Now, if you compare now this Dirac equation with the free Dirac equation, realize that one can obtain the one from the other by substituting the derivative with the derivative minus I mu, which is exactly the change that we were obliged to make. So changing from the derivative to the covariant derivative in order to make the Qed Lagrangian gauge invariant. Okay, so everything is consistent, but you are essentially see the same thing from two different sides. Okay. Now, this interactive equation, okay, which encodes an interaction between the fermion field and the photon field, or the electromagnetic field, to be more general, you can derive by starting from this Hamiltonian, where we have the unperturbated Hamiltonian plus an interaction term, which is an electromagnetic potential energy term. And it turns out, this we will not derive, but it turns out that you can write down the electromagnetic potential energy in this way in terms of the electron charge, minus E, and the photon field, the electromagnetic field, or if you like, these 4 potential MO. Okay. And since this is the photon field, we can use here indeed the wave function of the photon that I showed you before, which is given in general by a plane wave times a polarization vector. So this is our starting point, okay? So we have this Hamiltonian with this electromagnetic potential term, and let's now try to proceed in order to calculate the transition matrix, so the transition amplitude matrix for this process, which is indeed the Molar scattering. So an electron scatters with an electron, and in the final state you have again an electron and an electron. So the matrix element for the Molar scattering can be obtained by describing the interaction at the upper and lower vertices in terms of the potential energy that we just give. Now let's follow the UCAV approach, okay, that we know already. So following UCAV approach, the matrix element of this whole process consists of 3 parts. The strength of the interaction at each vertex, so for the upper vertex, characterized by 4 momenta P1 and P3, the strength is given by this matrix element, okay? This is the final state, this is the potential energy, this is the initial state. And for the lower vertex, again, we have the same thing. So this is the final state, this is the potential energy, this is the initial state field. And in between, of course, we need to put the propagator, okay, the bosonic propagator, as we did for, as we already mentioned before for the UCAV approach. Now, okay, in order to get indeed this transition matrix element, we have to compute all these objects here. Okay, so let's do this now on the board. One moment, let's try to activate these. Okay, can you see the whiteboard?
Yes.
Okay, so let me draw again the Famine diagram for the Molar scattering. Okay, so we have an incoming electron, an outgoing electron.
Mi scusi, potrebbe ingrandire la pagina?
Purtroppo no, perché se io allungo questo, la parte bianca rimane sempre uguale.
Ah, ok, va bene. Grazie lo stesso.
Provo a scrivere un po' più grande, dai. So we have incoming photon, incoming electron, outgoing electron in the upper vertex, the same in the lower vertex, so E minus, E minus. Then we have the exchanged virtual photon. Now let me put here the 4 momenta. So it's P1 for the incoming electron, P2 for the other electron in the initial state, so the 2 electrons that are scattering in the initial state. And then for the final state, we have P3 and P4. And let me also label the 2 vertices with 2 index. So this we will call mu, and this we will call nu. Okay, so this is all what we need. And now we have to compute each of the 3 terms. So the strength at the upper vertex, the strength at the lower vertex, and the photon propagator. Let me start from the upper vertex. So this is the object we need to compute. Si vede abbastanza bene così?
Sì, sì.
Okay. Okay, this we can write, of course, in an equivalent way as the Emission conjugate spinor. Then we have our electromagnetic potential energy, and then we have our spinor for the initial state. Let's now substitute all that we know. So for the Emission conjugate spinor, we put it explicit in terms of the U spinor for the electron and the plane wave part. For P3 is a 4 momentum, okay? Then we substitute here the expression of the electromagnetic potential energy that I gave you in the previous slide. It is minus E, gamma 0, gamma nu, epsilon mu, lambda, E to minus IQ dot x, And then we have the initial state spinor. So UE P1 E to I P1 scalar X. Now let's make some trivial algebra. So this is the complex conjugate, P3. Then we put here the electron charge. Then we have gamma 0, gamma nu, epsilon, mu, lambda, which is the polarization vector, and the initial state spinor. And let's collect here all the exponentials. So minus I P3 dot X. Now Q, you can write, is the momentum transfer. Okay, so this is a T channel, if you remember. So Q is the momentum transfer, is P1 minus P3 scalar X, and then E to I P1 scalar X. All right? So next passage, so this guy here stays the same, and here we just have E to minus I P3 plus P1 minus P3 minus P1 scalar X. So overall, this is E to 0, so this is just 1, okay? And so we are just left with the following result. So our strength at the upper vertex is nothing else than U daga E P3 minus E gamma 0 gamma nu epsilon mu lambda U E P1. All right? And then we can do the same for the lower vertex. Of course, we will not repeat the calculation. Let me just give you the result. So this is U daga E P4 minus E gamma 0. Sorry, this should be mu, not nu, because we label the upper vertex as mu. So this is a mu also here, everywhere. This is gamma nu. Epsilon nu star is the complex conjugate polarization vector, and E P2. So now we have this first two terms. We have to put everything inside the matrix element and include the Boson propagator. Ditemi se posso cambiare pagina, se ci siete tutti, se c'è qualcuno che deve ancora copiare. Ok. Okay, so let's write down now the expression of the full matrix element, MFI. So we have our upper vertex, the propagator, which in the very basic Yukawa approach is Q squared minus M squared, and psi P4, V EM, psi P2. Okay, so this is the matrix element the way Yukawa would have written it. Okay, of course we have zero mass for our photon. Now let's sum over all possible polarization state of the photon. Okay, so this is the sum over, and we substitute what we got before. So U daga P3 minus C gamma 0 gamma mu epsilon mu lambda UE P1. Then we have our propagator, which is just 1 over Q squared, and then we have the lower vertex, U daga E P4 minus C gamma 0 gamma nu epsilon nu lambda star U E P2. Now we collect all the polarization vector altogether, and we single out the rest. So this is U plus P3, E, gamma 0, gamma mu, UE, P1. Here we put the sum over all polarization vector. Divided by Q square. And then we have U dag E P4, E, gamma 0, gamma nu, UE, P2. Now, a few more passages. So this we can write as E, U dag P3, gamma 0, and then we have gamma mu, UE, P1. This is just, if you remember, minus G mu nu divided by Q square. And then we have also here E, U dag E P4 gamma 0, and then we have gamma nu UE P2. Now we remember that this is the adjoint spinor, right? And also this one here. And so we can write our transition matrix element as, we have a minus sign here on top of a G mu nu, so this is minus E square, and then we have U adjoint P3, gamma nu, UE P1, G mu nu over Q square, and U adjoint P4, gamma nu, UE P2. Let me call this equation 1. So what we obtain here is indeed the transition matrix element for the Molar scattering, okay? Electron scattering. Now we can write this in a more compact way, because we recognize that this here is nothing else than the 4 current, J mu, and this is the 4 current at the, so these are the upper vertex, and this is J nu at the lower vertex. So we can write down this matrix element in a more compact way as minus E square. We have G A mu, then we have G mu nu, G A nu over Q square. Okay. Now you remember that when you multiply a contravariant for vector with G mu nu, you get the covariant for vector. So back in our first lesson. So this is minus E square, and then you have now both. So one is contravariant, one is covariant. So this is J mu, contravariant, E, and this is now E mu, yes, divided by Q square. So this is the action of G mu, of the metric tensor over this contravariant tensor vector. But G mu is now nothing else than the scalar product of the two vector currents. So this you can write at the end as minus E square, and then GE, let's put mu in parentheses to indicate that this corresponds to the upper vertex, scalar GE of the lower vertex, okay? So these are not anymore Lorentz index, just to indicate that one is for the upper vertex, the other is for the lower vertex, and Q square. So overall, we managed to write down the expression of the transition matrix element as the scalar product of the two vector currents, one for the upper vertex, one for the lower vertex, divided by Q square, and then multiply by minus E square. But we can write down this matrix element also in another convenient way. Let me write it down here on the bottom. So suppose now you multiply this by minus I. Okay, let me take a new page. I need more space. So let's multiply this by minus I. So we're going to have, starting from equation 1, the one I wrote before, okay? So we are left with mu E P3 I E gamma mu UE P1 minus I G mu nu over Q square and UE adjoint P4 I E gamma nu UE P2. Okay, so we just started from the expression 1 that I gave you before, and we multiply by minus I. So the minus I now enters here into the propagator. And so the advantage of writing the matrix element this way is that you recover indeed the full expression of the photon propagator and the two vertex factors that will be understand better later on with the Famine diagrams. So this is the vertex factor for the upper vertex, and this is the vertex factor for the lower vertex. So, in other words, we started from very first principle, so essentially from the Dirac equation of electron field in electromagnetic potential. We adopted the Yukawa approach, okay, which was proposed already in 1935. And by doing simple algebra, we derived the matrix element for the Molar scattering, okay? And so we write down in a compact way in terms of the scalar product of the two currents of the upper and lower vertex, but also in this more explicit way, where indeed you have explicit the photon propagator and the two vertex factors. And this is indeed the way you see it written here, the conjunction between this first principle approach with the approach based on the Feynman rules that will be developed in a moment. Okay. Any questions? Okay. So if there are no questions, let's get back to the slides. Okay. And let me summarize in this slide what we achieved on the blackboard, on the whiteboard, whatever. So by summing over all possible polarization state of the virtual photon, we found that we can write the transition matrix element in this way. This was our equation 1, or in a compact way in terms of the scalar product of the two currents at the upper and lower vertex. Or if we now multiply by minus I, we can make explicit here the photon propagator and the two vertex factors. And this will become clearer, let's say, in 10 minutes from now. Now, still on the Molar scattering, this is not the end of the story, because at the lowest order, in the perturbative expansion, the Molar scattering is described also by a second diagram that you see here, okay, where both are T channels, where the final state particles, which are undistinguishable, are both electrons, are now interchanged. You see? Now, the electron field coming from the upper vertex has for momentum P4, and the electron field coming from the lower vertex has for momentum P3. Okay? Since you can never be able to distinguish between these two electrons, so you have to take into account both diagrams and their interference in principle. So if you want now to make the transition matrix in a full form, including also the second contribution, which is as important as the first one, because they both appear at the first order in the perturbation expansion, you just need, you can write the second matrix element, starting from the first one, and just substituting UP3 with the UP4. You just need to make this very minor change. Otherwise, all the rest is the same. And you need to account also for a relative minus sign to account for the interchange of identical Dirac fermions. So this minus sign here, which becomes a plus because you have already a minus here, this is a consequence of the Dirac Fermi statistics. Okay. So at lower order in perturbation theory, your matrix element is given by the sum of these two contributions. Well, for instance, here the transport momentum is P1 minus P3, and here is P1 minus P4, because we just interchanged P3 with P4. And of course, also here and here. Okay. Now, to calculate now the unpolarized cross-section, so without any information about the electron spin, one, as we know already, as we studied already, one has to average over the spin of the incoming particle and sum over the spins of the final state particles. So at the end, we obtain the spin average transition matrix element squared. Okay, so we take the average, so we sum over the possible spins, and we divide by the total number of possible spins, which is given by the spin multiplicity, usual. Okay, and then we also have to sum over the final state spins. So we have a double sum here, and this is what provides you at the end the spin average transition matrix element square. The last step, we want to calculate the cross-section of this Molar scattering, is to put this into our general cross-section formula, the one that we derived a few lessons ago, starting from the Fermi golden rule, if you remember. Okay, so this is the differential cross-section, okay, with respect to the solid angle, and you have to substitute here your squared spin average matrix element. And at the end, you get your differential cross-section, and you can further integrate over the solid angle to get the total cross-section. Okay, we will come back to this. So now, let me conclude this discussion by saying that although deriving the expression of the transition amplitude for a given process, in this case, the simple Molar scattering, from first principles, so starting from the Dirac equation and then applying perturbation theory, although it is very instructive and provides a deep insight into the underlying physics at the fundamental level, the calculation is often quite complex and time-consuming. So we spend, let's say, 15 minutes or 20 minutes for the very simple Molar scattering. But if you want to calculate much more complex QED processes, starting from first principles, can take hours, or you might also need. Okay, I mean, it is a huge work. Okay, you can do it. You will obtain the correct result, but it's a huge work. However, we have another possibility, that is following the Feynman rules. The Feynman rules are formally proved in QFT. We will not prove these, of course. This you can find in quantum field theory courses. And by applying these simple Feynman rules, you can derive immediately the matrix element of any QED process. So let me draw you the Feynman rules, which are the rules to construct Feynman diagrams and to make a correspondence between any element of the Feynman diagrams and the matrix element, as I was mentioning at the beginning. So let's take this as an example, okay? So solid straight lines represent fermions, always, while wavy, curly, or dashed line represent boson. In this case, we have a wavy curve, which is for the photon, but you can also have dashed or curly, and this that use for the doubly bosons, for instance, or for the gluons, etc. Now, by definition, time increases from left to right. So in this case, this is the initial state, and this is the final state. An arrow indicating motion of a particle backward in time, such as this one here, okay? Time goes in this way, and this arrow points backward in time. This indicates an antiparticle moving forward in time, and thus it represents an antifermion. Okay, so in order to graphically distinguish between fermion and antifermion, we use the old prescription that the antiparticle moves backward in time. Okay, just to distinguish them graphically. Of course, both particle and antiparticle propagate forward in time, as we know. Now, fermion and boson lines meet at vertices. You find here two vertices in this diagram, okay, where charge, energy, and force momentum are conserved. Lines entering or leaving the boundaries of a diagram represent real or on-shell free particles. So all these objects here, which are external, 1, 2, 3, 4, are real particles. Okay, so on-shell particles. They fulfill the standard energy-momentum relativistic relation. Whereas line joining vertices, such as this one here, it is joining two vertices, represent virtual particles, so off-shell particles. That could be either bosons, but also fermions, as we will see in some example. Okay? And being off-shell, their mass does not correspond to that of the corresponding real particle. So if you remember, a virtual particle is off-shell in the sense that it does not fulfill the energy momentum relativistic rule. And this you can reinterpret it as saying that, for instance, the mass of the exchanged virtual particle is different than the corresponding real particle. For instance, if you remember, I was mentioning you that you can also interpret the virtual photon to be a massive object in principle, okay? Because it does not fulfill the momentum energy relativistic relation. Now, the strength of the interaction is represented by the coupling constant. So, for instance, for the Qed, so for the electromagnetic process, the coupling constant, as we will see in a moment, is given by the fine structure constant, the square root of the fine structure constant, which is proportional to the electric charge of the electron. Indeed, the square root of the coupling constants are involved at vertices, while propagators are associated to virtual particle exchanged between vertices. Now, in Qed, the fundamental interaction is between a single photon and two spin-off fermions, and there is no Qed vertex connecting more than 3 particles. Okay, so this is all that you need in order to write down correctly a Famine diagram for any Qed process, and making use of the Famine rule to write down the corresponding matrix element, and so the cross-section at the end. So these slides summarize essentially the Famine rules that I gave you before. Okay, so when you write down the matrix element with -I, it consists of 3 basic elements: the wave function, so it is essentially the spinor for the external lines, the propagators for the internal line, which are our virtual particles, and the vertex factors. Okay, so indeed, for the fermion, we have solid lines. Okay, which are moving forward in time for the particle solutions and negative in time for the anti-particle solution. These are, of course, Dirac spinors. Initial state photon and final state photon are provided in terms of the polarization vector, where the final state photon is the complex conjugate. The photon propagator we already derived, but we can also have a fermion propagator, which of course look a bit more complicated. We also have a non-zero mass to take into account. And then at each vertex, the strength is given by -I QE gamma nu, where QE means Q times the charge of the electron. So just to repeat, associated with each vertex is the coupling constant, okay, which is the square root of the fine structure constant, which is proportional to the electron charge, which, as already anticipated by Yukawa in 1935, indicates the probability of the emission or absorption of the exchanged particle, and thus it corresponds to the strength of the interaction at each vertex. There is another important thing that we have to consider. So Famine diagrams not only account for the summation over all possible polarization state. So when you have a Famine diagram like this one, it is implied that you are summing over all possible polarization state of your exchanged boson. Okay, but not only this. They also account for all possible time orderings. So let's see what does this mean. So consider these two processes, okay? These two electromagnetic interaction where 2 electrons exchange a virtual photon, okay? So in the first diagram, so the time, as usual, goes from left to right. Let's consider the first diagram here. So in the first diagram, the lower electron emits a photon, which at a later time, okay, this comes later than this, it is absorbed by the upper electron. And the overall effect is a momentum transfer between the 2 electrons. Let's now consider the second. This is the opposite. So in this case, this corresponds to the other possible time ordering, where now is the upper electron that emits the photon, which at a later time, it is absorbed by a lower electron. Okay. Now, since the exchanged virtual photon is not observable, it is a virtual particle, okay? So you will be never able to distinguish between the two. And only the combined effect of all possible time order diagrams, or if you like, the sum of all their amplitudes, is physically meaningful. And this is what indeed we mean by Famine diagrams, okay? So the Famine diagram, which is the last one, is the only real one, includes the sum of all possible time ordering. So the left-handed side in this case represents the initial state. The right-hand side corresponds to the final state without specifying which particle emits and which particle absorbs the photon. Okay? So to summarize again, the Famine diagrams take into account the sum over all the polarization state of the emitted boson, as well as the sum over all possible time orderings. Okay? Now, let's now repeat our calculation of the matrix element for the Molar scattering, but now making use of the Famine rules. Okay, and so let's do these step by step. And once you get familiar with these, you can do it in a couple of minutes, of course. So let's take the Molar scattering as an example, but this is, of course, general. Okay. So first of all, let's draw the Famine diagram with the minimum number of vertices. Of course, there may be more than one. As we've seen for the Molar, indeed, we have the other diagram at first order. So for this diagram, we have two incoming electrons in the initial state, an exchange at the virtual photon, and two outgoing electrons in the final state. Pay attention that the arrows are only drawn on external lines and represent particle flow, forward in time for antiparticle and backward in time for particle. So they do not represent the momentum flow. Okay, it's just a way to essentially to describe particles and antiparticles. In this case, they are all forward in time because we are dealing with electrons, which are, of course, particles. Now, for each Famine diagram, label the form momentum of each line. So it is very useful to put now the form momentum for each of the incoming fermion, and enforcing for momentum conservation at the vertex. This corresponds to enforce the correct form momentum for the virtual photon. This is a T-channel, so this is indeed given by the difference of P1 minus P3 or P2 minus P4. Step 3. Every Qed vertex contributes with a vertex factor, the one that I tried to highlight before when we write down the matrix element expression multiplied by minus I. So for any Qed vertex, the vertex factor is given in this way, where Ge is a dimensionless coupling constant, which is related to the Fine-Structure constant. So the relation is given here. The Fine-Structure constant that you can write in a full shape in terms of the squared electron charge is Ge squared divided by 4 mu. So this is the relation between the, let's say, the Fine-Structure constant and the coupling constant for the Qed interactions. And so you see here already that Ge is proportional to the electron charge. So when you now use natural units, so h bar, c, epsilon 0, this all goes to 0, or to 1, sorry, then it turns out that indeed Ge is minus E, where E is the electron charge, which is proportional to the square root of the Fine-Structure constant. Okay, so in this case, indeed, our generic vertex factor can be written as I E gamma mu, where we just replaced in Ge equal minus I minus E. Okay, and this is proportional again to the square root of alpha. So at each vertex, the probability of the emission or absorption of the photon at each vertex at the end is proportional to the square root of the Fine-Structure constant. Now, let me open a parenthesis here. So in the language of the quantum field theory that we just very quickly introduced, the process occurring at the vertex is interpreted as the initial electron field is destroyed by an annihilation operator and disappears at the vertex. At the same time, the creation operator creates the final electron field and the photon field. Okay? And asking whether the initial and final electrons are the same or different particle is meaningless because all electrons are identical. So this is how you would interpret this process in terms of the quantum field theory language. So in terms of annihilation and creation operators. All right? Now, we are not done yet. Step 4, each vertex contributes with a fermion current, okay, which you can construct in the usual way. So it's given by the adjoint spinor for the final state particle, so this one in this case, so U bar P3, the vertex factor in between, and the spin for the initial state particle, P1 or P2 at the bottom, okay? And it is also convenient to label the two vertices as mu and nu. so that you can use the proper Lorentz index in the two vertex factors. Okay. Now, the last ingredient is the photon propagator, okay, which, as we know, is given by -I g mu over q squared. And so now we have just to put everything together. Before that, let me again point out that in this simple case, the propagator is that of a photon, but you might also have processes where you are propagating a virtual fermion. In this case, the propagator will look a bit more complicated, and we will see some example later on. So now we put everything together, okay? So we multiply the current at the upper vertex, the fermion propagator, the photon propagator, and the current at the lower vertex, and indeed, by simply doing so, you already have your expression for the transition matrix element. You can further divide by -I, so you get rid of this and this, and you obtain the full expression like this. Okay. So by simply applying the Feynman rules, we don't have to start from the Dirac equation to make the energy potential, to make all that algebra. You just have to plug the three main ingredients, the two currents and the propagator, and you're done. And as we have seen already, this matrix element can be written in a more compact way in terms of the scalar product of the two vector currents. Okay. So again, we make use of the metric tensor, okay, to end up with the scalar product at the end. So we can write it here in this way. This is a T-channel, so we are allowed to substitute Q square with the T Mandelstam variable, okay, which is defined in this way. Now, as usual, this is not the end of the story. Before going on, let me go first to this point here. So this was again the Molar scattering, okay? So electron that goes into electron. So we only use the particle spinors or particle adjoint spinors, so the U spinors. But suppose you have now a process like this, okay? This is a E plus E minus annihilation process that turns out into a mu plus mu minus at the end. These are muons, okay? Of course, you can also apply the Feynman rules to construct the matrix element of this process, but now we have to consider that you also have antiparticles in your game, okay? So for instance, when you write down the matrix element, this is a positron, so this is an antiparticle. So here we have the adjoint of the antiparticle solution, whereas the other one is a particle solution. And the same for the final state. Yes?
I'm sorry, excuse me. I don't know if that's my problem, but the connection just jumped and I lost completely all the phrase that you were saying.
Chiediamo agli altri, ragazzi, voi avete perso qualcosa?
Io non trovo.
Avete tutti visto tutto tranne la ragazza che ha parlato adesso? Giro la domanda, c'è qualcun altro che ha avuto un problema di connessione?
Io ho sentito tutto.
Ok, allora probabilmente è un problema. Ok, quindi è un problema della tua connessione, probabilmente.
Ok.
Se mi dici la parte che ti sei persa, la ripeto velocemente.
No, solo l'ultima frase che ha detto.
Ah, va bene, ok, è stata una cosa temporanea.
Sì, assolutamente.
Ok, so let me just, quindi questa slide qui, giusto? La slide 20?
Sì, esatto.
Ok, la ripeto volentieri.
Grazie.
So let's now consider this different process, okay? So we have now an annihilation process, which now involves not only particles, like the electron and the muon, but also the corresponding antiparticles, the positron and the positive muon, okay? So in this case, when you write down the matrix element, you have to take care that for the antiparticle, you have to use the V spinors, so the solution of the Dirac equation for antiparticles. And this, of course, occurs at the initial state and also in the final state, okay? That's it. And then you can divide by -I and you obtain your matrix element either in the full expression or in the compact way as the scalar product of the two matrices, the two currents. Now, you might wonder, how can I decide whether the adjoint spinor must be the antiparticle or the particle? Why we don't have here U bar P1 and here V P2, right? So there is a mnemonic rule, okay, which is, of course, one of the Feynman rules, and it is the following. So the first particle encountered when following a fermion current from the end to the start in the direction against the sense of the arrows always appears as an adjoint spinor. So what does it mean? Let's go back to the diagram. So in this case, let's consider the initial state. In the initial state, the direction of the current is this one, okay? Is the one given by the arrows in the diagram. So from the top to bottom. Now we take the other the opposite direction. So let's start from the top, from the bottom to top, as indicated by the red arrow. And the first object that you encounter in this opposite, so going opposite to the flow of the current, the first object must be adjoint. So in this case, is the first object that you encounter in this bottom to top direction is the positron. So it is the antiparticle spinor that must be adjoint, and the other is not adjoint. Similar for the final state. Okay, in this case, the current flow is from bottom to top. So we take the opposite direction. We start from top to bottom, and the first that we encounter, which is now a particle, should be the adjoint one. And in this case, the antiparticle is not. Is that clear? So keep in mind this mnemonic rule in order to write correctly your matrix element, okay? So to be sure that you put the correct spinor as adjoint and that everything is consistent. Yeah, ok, we can make a break now. Una pausa, ricominciamo alle 10:15. Ok?
Ok.
Ok ragazzi, riprendiamo. Dunque, sono sharing. Ok, mi confermate che vedete la slide?
Sì, prof.
Ok, allora riprendiamo. So, we derived the matrix element for the Molar scattering, electron-electron that goes into electron-electron, both from first principles and by using the final rules. Okay. Let's now concentrate on this process here. So this is E plus E minus annihilation that goes into a muon pair. Okay, and let's derive this, the matrix element for this up to the derivation of the cross-section, and at the end we will compare with experimental results. Okay, but you have to be careful, because in calculating the cross-section for a given process, now in particular we are considering this, but this is a very general argument, the transition matrix has to be evaluated by taking into account all possible spin states of the particle involved. So let's see what does this mean. So since each fermion has two possible helicity states, either positive or negative, there are in total 4 possible helicity configurations in the initial state. So the initial state is the electron-positron annihilation, okay? So let's consider the first one is where the momentum and the spin are aligned, so this is a positive helicity, or where the momentum and the spin are anti-aligned, this is a negative helicity. And then we have all 4 combinations, plus minus, plus plus, minus minus, minus plus. This is for the incoming particles, but of course the same you have in the final state. So similarly, there are 4 possible helicity configurations in the final state for the 2 muons. Therefore, the process overall consists of 16 possible orthogonal helicity combinations, each of which constitutes a separate physical process. Okay? So, for instance, the first one is E plus that goes into mu plus mu plus. The second is E plus that goes into mu plus mu minus, etc. You have 16 of these. And so, in principle, you have to calculate all of them. Now, for a given initial state helicity configuration, suppose we concentrate on the plus plus, so both electron and positron have a positive helicity. Then we have 4 possible final state helicity configuration, and the total cross-section is obtained by summing over all the 4 corresponding squared matrix elements. So for the plus hypothesis, this is our matrix element. This is given actually by the sum of the 4 matrix elements corresponding to the 4 different helicity combinations in the final state. Okay, so in the initial state we have always plus plus. In the final state we might have plus plus, plus minus, minus plus, minus minus. Now, if we do not select the polarization of the initial and final state particles, okay, we have, as usual, to average over the polarization of the initial state and sum over the polarization of the final state, okay? So, and this is indeed what has happened in most of the cases. So, in most of the E plus E minus colliders, the colliding particles, the colliding beams, are not polarized, so they are unpolarized. This means that the 4 initial state helicity configurations are all equally probable. There is not a specific spin configuration. They are all probable. This means that the beam is unpolarized, okay? And this is accounted for by defining the spin average squared invariant amplitude, okay, in the usual way. So we take the sum over the initial state spins, the average of the initial state spin, and the sum over the final state, okay? So for the average, you have to sum them and divide by the total, which is given by the spin multiplicity. And for the final state, you have to sum again over the final states. Now, if you put here 1/2 for the spin of the electron, okay, this factor is just 1/4, okay? So overall, this you can write in this way here, where the sum spans over all the 16 helicity configurations. Now, back to one of our previous lessons, okay? If you remember, we showed that chirality is conserved in all electromagnetic processes, or more in general, in all processes that require a vector current, okay? So as a consequence, as we have seen, vector currents made by 2 particle spinors or by 2 antiparticle spinors are 0 for the mixed chirality cases. Okay, if you remember, we developed our vector current each spinor can be always decoupled into a left-handed and right-handed chiral states. And then we made all the product, and we are indeed 4 contribution. And we showed up that the mixed contribution, so left-right or right-left, are always 0. And the only 2 surviving are the pure contribution, left-left or right-right. And this corresponds to say that in electromagnetic processes, which are based on vector currents, chirality is conserved. Okay, so the chirality enter the vertex is the one as that exiting. Now, since now in ultra-relativistic limit, okay, where we can neglect the masses, or so we can assume that the particles are massless to a very good approximation. If you remember, the chiral eigenstates coincides with the helicity eigenstates. And so we can write down this expression here in terms of the helicity eigenstates. So U minus gamma mu U minus plus U plus gamma mu U plus. Okay? So in the ultra-relativistic regime, U minus corresponds to U left, and U plus corresponds to U right. And so, as we've seen already, in this case of ultra-relativistic scattering process, only the following possibilities are allowed, okay? Essentially these two, the pure. So the one where the helicity leaving the vertex is the same as that entering. These positive helicities where the spin and momentum are aligned, and this is also positive at the end. This is negative, and this is negative at the end, okay? This is for fermions, and you have the analogous for the antifermions, where the only difference is that, as you know now, in the Famine Diagrams, the antifermions arrow is backward in time. So, these arguments can now be extended to the case of the annihilation per production process, like the one we are studying now, okay? This is a bit different case, because the currents now involve also antiparticle spinors. So, let's make a step backward. So this holds for current which only involved particle spinors, U, okay? Now, let's consider our case where we have a plus E minus annihilation into mu plus mu minus. So in this case, the current involves an antiparticle spinor and a particle spinor. These you can always decompose into left-handed and right-handed chiral states. But now, so you always get 4 contribution. But now, if you do the calculation, we will not do this, but you can do as an exercise, we found out that in this case, when we have an antifermion and a fermion field, the pure terms cancel and only the mixed terms survive. Okay? And this we can again write in terms of the helicity spinors. Okay? So for the current that we need for describing our process with an antifermion and a fermion, this we can write approximately, so assuming that we can neglect the masses, in terms of the helicity spinors. So V minus U plus or V plus U minus. And this is the situation now for our case, okay? So in this case, the outcoming or outgoing fermions at each vertex have opposite helicity, okay? And all other combinations corresponds to helicity non-conserving processes, and so corresponds to null currents. Okay, so all the other U minus, U plus, U plus, U minus, V minus, V plus, V plus, V minus, or mixed, but now with the same helicity, V minus, U minus, or V plus, U plus, these are all 0. Okay, and this, of course, simplifies a lot the calculation of the matrix element and in turn of the cross-section, because we have to take into account only few terms. So, again, in the ultra-relativistic limit, where we can neglect the mass of the electron and the muon, chirality conservation implies that only 2 of the 4 helicity combinations for both the initial and the final state lead to non-zero currents, okay? Which are indeed the mixed one, because now we have an antiparticle spinor and a particle spinor. So the only 2 surviving in the initial state are plus minus, okay? Okay, I wrote it the opposite, okay. I will correct this in the slide. So this is minus plus and plus minus. And the same you have for the final state, okay? So only 2 out of 4 survive. So essentially only 4 currents out of 16 will survive. And here, let me remind you that these V minus, V plus, V plus, V minus are the helicity spinors that we already introduced when we discussed the Dirac theory, okay? Where C and S are the cosine of θ². So if you go now back to our process, so E plus E minus into mu plus mu minus, so only 4 helicity configuration result in a non-zero matrix element, okay? and thus only 4 of them contribute to the cross-section of the process. Okay, so let's consider the first one. We have E minus E plus in the initial state. One has a positive helicity, where the spin and the momentum are aligned, and the other have opposite helicity. So this is the plus-minus case for the initial state. And in the final state, we have positive helicity for the muon, they are aligned, and negative helicity for the anti-muon. So this is the case of plus-minus into plus-minus. And then you have all the other 3 combinations. So plus-minus into minus-plus, minus-plus into plus-minus, minus-plus into minus-plus. Okay? These are the only 4 that contribute to the real process. All the other corresponds to 0 current, and so to 0 matrix element. Let me also note that in all cases, the spin of the initial state and of the final state particle are aligned. So the spin is the black arrow, okay? You see, the helicity is opposite, but the spin is always aligned. So in this case, they are both in the right direction. Also in this case, they are both in the left direction. And the same for the 2 final state muons. So the spin are always aligned. This means that since they are fermions, each coming with a spin 1/2, this means that the initial state has always spin 1 or -1. And also the final state has only spin 1 or -1. And this is exactly what we want, because we know that the particle that we are exchanged, which is a photon, is a vector particle, so it has a spin 1. So in order to have angular momentum conservation, this is indeed exactly what we need. Okay? We have spin 1 or -1 initial state, spin 1 or -1 in the final state, which makes sense because we are exchanging a spin 1 particle, the photon. So back now to our average squared matrix element. So we have in general 16 terms, but most of them cancel because of chirality conservation in electromagnetic processes, and only the 4 of them survive. So at the end, we just have to sum only these 4 objects here. Okay, and once we do so, okay, well, each of these terms we can write as a separate process. So in terms of the scalar product of the 2 currents, where now these index x, y, z, k are either plus or minus helicity. Okay. Now, by inserting the full expression of the helicity spinors that I gave you before, okay, so in terms of the theta angle, and by performing the scalar product of the currents, so for each of these terms, you perform this scalar product, okay, you end up with this expression, okay. So for 2 of them, plus minus into plus minus and minus plus into minus plus, the squared matrix element gives you this kind of angular dependence, where theta is the angle of the outgoing mu minus with respect to the incoming E plus direction in the center of mass. For the other 2, plus minus into minus plus or minus plus into plus minus, it is essentially the same, but with a minus sign here, okay? We will not derive this, but it's a trivial algebra once you put the full expression of your helicity spinors based on polar coordinates. So now we can sum up all of them, okay? So 2 by 2, because 2 of them are equal, so it's twice this guy plus twice this other guy here, okay? And so you do some very trivial algebra. At the end, you can write down your spin average squared invariant amplitude as e to the 4, 1 plus cos square theta. There is an equivalent way to write down this matrix element, which is in terms of the Mandelstam variable, okay? And which is now, of course, explicitly covariant, because the Mandelstam variable are all Lorentz invariant. So an equivalent way to write down this is in terms of t squared plus u squared divided by s squared. We will not show this, but this can be shown easily, okay, just with some algebra. So now the next step is to substitute our spin average squared matrix element into the differential cross-section, okay? This is the general formula that we derived starting from the Fermi-Condon rule a few lessons ago. So we now substitute our expression for mfi squared, and we can simplify. We can now define the fine structure constant as e squared divided by 4 pi in natural units, as we mentioned before. And so at the end, we end up with this simple relation where we simplify the 2 momenta in the center of mass because they are essentially equal in the ultra-relativistic limit. So this is at the end our expression for the differential cross-section with respect to the solid angle. Let's now plot this as a function of cos theta, okay? So it is a 1 plus cos theta, so it is a parabola in this diagram. So you have here the differential cross-section and as a function of cos theta. And you can say that this parabola is actually the convolution of the two contributions, okay, that I showed before. Essentially, this one, twice this one, plus twice this one, okay? So these are the two contributions separated, and then the convolution, which is our total differential cross-section. How does this compare with experimental data? So the point here that you say here are experimental data with the error bars that have been measured at the Jade experiment at Petra, okay, in the 80s. And the solid curve is the one coming from our calculation on Qed, okay? So what would you conclude from this plot here? You would conclude that, okay, the agreement is rather good, but it is not perfect, right? Because the points are not on the solid line, but they follow this dotted line. This appears to be a failure of our calculation, but instead it is a strong confirmation of not only our calculation of Qed, but of the standard model in total. Because in reality, okay, we have to take into account that our first order Qed diagram, where a photon is exchanged, interferes at high energy with the equivalent Famine diagram, where now we have a neutral current weak interaction by exchange of a Z0 boson, as we will study next in the course, okay? And if you take both into proper account and their interference, then you end up with the dotted line, which is indeed extremely well, we describe very well our experimental data, okay? So the dotted curve includes the electroweak correction, which interferes with the Famine diagram involving the exchange Z0 with boson. And this contribution here, as we will study next, becomes important at a large energy. So at the energy of the center mass energy of the order of the mass of the Z0, so at the 90 GeV or something. If, on the other case, you perform this experiment at lower energy, this contribution here becomes negligible, and indeed your data will follow the curve based only on the photon exchange. Chiaro, ragazzi? So yes. This apparent discrepancy is indeed actually a proof that the standard model works very well. Now, let's integrate this differential cross-section over the solid angle, okay? So we have to integrate this part, which depends on theta, over the omega, which is given by the phi, the cos theta. The integral over the phi gives you a trivial 2 pi. And once you do the integral, overall you obtain this number, 16 pi divided by 3. So you substitute this into your cross-section. On top of this, if you remember, we have this factor here, okay? And so this is, at the end, the expression of the total cross-section for the plus-minus annihilation process as a function of energy. Why? Of energy, because this is a function of the S Mandelstam variable, which is, as you know, the square of the center of mass energy, okay? You can also put numbers here. You put the experimental value of alpha, you have for your pi, you have 3. So if you put numbers, you can write this in terms of only of the S dependence, okay? And you will get the results in JEV at the end. So if you put, you get your result in nanobarn if you express your S in JEV squared. Let's compare again this with experimental data. So now this is the total cross-section in nanobarn, okay? Again, for this process here, E plus E minus into mu plus mu minus. And the curve that you see here is indeed given by this quantity here. So our total cross-section as a function of S. This is indeed reported as a function of square root of S, okay? And you see that indeed the data now coming from different experiments are in very good agreement with our prediction based on a first-order Qed calculation. As we will study tomorrow, okay, this is not the end of the story, because this is only the first order, but we have an expansion, okay, a perturbation expansion. So in order to make more precise predictions, we have, of course, to include also the contribution from the higher orders, second order, third order, etc. Okay, this will be studied tomorrow. Now, c'è qualcosa?
Yeah, just a question before we go. If we align the spins of the particles before, can we just measure with just part of the matrix elements?
Indeed, exactly. If you align your, so suppose you do two things. You provide a polarized beam, okay, with this, your electron beam and positron beam with the spin or both aligned in the same way. In this case, you don't have to average over the initial state. You just have one possible spin combination, which is the one you prepared for your machine. Okay. Similarly, for the final state, suppose that you have a very highly performant polarimeter, so that you can measure the spin of the final state. Okay. Then you can consider essentially only one spin state, the one that you are interested in, for instance, for the final state. So indeed, as you say, for your prediction, you have to consider only the spin combination that you need in that case.
Okay. And has it been measured? Has there been an experiment to do?
I think so. I don't have a result now, but sure it has been done. Well, there are not many examples of polarized. There are not many examples of polarized electron-positron collider. I'm not sure actually. For sure, there have been polarized electron-proton scattering measurement, QED measurement. This is for sure, and we will also study this in the second part of the course. So polarization measurements are done, of course. I'm not sure if in E plus E minus collider, but for sure in E minus proton collider, or in pixel target experiment as well. This we will study, of course, in the course. So in that case, you only have to pick up your contribution of your matrix element that corresponds to the spin that you either prepare in the initial state or you measure in the final state.
Okay. Thank you.
Okay. Now, okay. So far we made, let's say, kind of complete and sort of rigorous derivation of the matrix element and of the cross-section for the Molar scattering, essentially, and also partially also for this annihilation process. In the following, let me just show you very quickly, so without going into the detail of the calculation, how to extract the cross-section for other relevant QED processes. Okay. So I don't pretend from now on that you follow everything. I will not ask you these are the exams, of course. It's just to give you an idea on how to calculate other more complicated QED processes. Okay. First of all, so yeah, let's start with the Baba scattering. The Baba scattering is now E plus E minus into E plus E minus. Okay. And in this case, there are two processes which contribute to our result. Okay. One is an S channel and the other is a T channel. And having the same initial state and final state particle, these two diagrams must indeed interfere. Now, the matrix element for the first diagram is equivalent to that we already derived for the E plus E minus annihilation. Okay, so this is indeed equivalent. We just have E plus E minus instead of mu plus mu minus. So everything is the same. So here we have to take into account the antiparticle, of course, the antiparticle spinner, etc. So this is just nothing else than replacing electrons and positrons instead of mu plus mu minus. For the second, this is now a T channel, okay? So indeed, the matrix element for the second will be very similar to the Molar scattering one, okay? E minus, E minus, and E minus, E minus. The difference now is that we have antiparticles, okay? So in the upper vertex, we only have electrons. So this is only, sorry, this is a U bar. You have to correct this, U bar, U. And in the lower vertex, we have only antiparticles, so V bar, V. And then, of course, you want to make them, you want to put them together because the two have to interfere because the final state particles are the same, so you cannot distinguish between the two. And you have to take also, we have to put again a minus sign here, which arises from the Fermi statistics. So this is the way, essentially, taking the difference of these two is the way to calculate the matrix element for the Baba scattering. Now, we have to account, of course, also here for the helicity configurations, okay? So in this case, there are, we have 6 different Relativistic configurations. Some of them involve only one diagram. Some other involve both diagrams. We will not derive these in detail, of course. But as a result, in the case of an experiment with unpolarized beam and where no polarization measurement is done on the final state, again, we have to average all of them. Okay, so this is our average squared matrix element. And we can write these again in a compact form in terms of the Mandelstam variable. So what we see here in this compact way is that this term corresponds to the first diagram, this term to the second diagram, and the last term from the interference between the two. Now one can make things even more explicit. So one can show that the T and the U Mandelstam variable can be written in terms of the polar angle in this way, by substituting the 4 momenta in the spherical polar coordinates. And so at the end, I will skip the passage, but I don't care about the passages. At the end, one can write down the average square matrix element in this way in terms of the theta angle. So now we put this into our general cross-section formula, as usual, okay? And we can now compare with results, okay? Now, the full prediction is, in this case, the black, the full line, okay? And as you see that in this case, we have a perfect agreement between the prediction and the data, okay? The distinction between the full and the dotted line we will see tomorrow, okay? So for the moment, let me skip this. Let me just say that with this Qed prediction, we are able to indeed predict very, very precisely our experimental data. Consider that we have a logarithmic scale here, okay? So indeed, the agreement is extremely high. Now, the agreement indeed between the Qed prediction already at first order, we are not including higher order correction, so also this is important to note. So the agreement between the Qed prediction and the experimental measurement is so high that this process is often used to determine the beam-beam luminosity in the plus-minus colliders, or the beam target luminosity in fixed target experiment. Okay, so what, for instance, in a fixed target experiment, suppose you have a target of whatever hydrogen, whatever. Okay, you have an electron beam, so you study the scattering between the electron beam. Oh, suppose we have a positron beam. Okay, let's consider the case of a positron beam on a hydrogen target. So you study the scattering of your positron from the beam and one of the atomic electrons in your target. So you have an E plus E minus scattering. You know precisely how to calculate the cross-section, okay? And so by measuring this cross-section and comparing with the prediction, you have a very precise, you get a very precise estimate of the luminosity of your collisions. And similar, of course, you can take in E plus E minus collider. Okay, in this case, you consider the E plus and E minus from the two colliding beams. Now, let's now move on to another process, Qed process. This is the Compton scattering that you all already know. So this is a scattering of a real photon over an electron. And the difference with respect to what we have seen in the past is that now the virtual particle is a fermion. It's not a photon, but it is an electron. Okay. So this process includes a real photon and a virtual electron, as well as real electrons, of course. So the propagator is a bit more complicated, okay, because we have to take into account not only the 4 momenta, which is given by the sum of K and P, but also the mass of the exchanged virtual fermion, okay? What about the real photon? So for real photon, we use the wave function of the photon, of our photon field, which is indeed the polarization state and the plane wave, where now K is our 4 momentum for the real photon. And we put everything together in the usual manner, okay? So for this is, for instance, for the at this vertex here, this is the current at this vertex here, where we have our fermion spinor, then we have the vertex factor, I, E, gamma, mu, and then we have the photon spinor. It turns out that these exponential cancel in the two, so at the end you only have to take into account about the polarization vectors. Then in between you have your virtual electron propagator, okay, where P and K are indeed the 2 components of the 4 momentum of the exchanged virtual electron, and M is the mass. And then finally you have the second vertex, the final state, and the final state. So in this case, you have the U bar P prime for the real electron, and the complex conjugate polarization state for your real photon in the final state, and in between, as usual, the vertex factor. So I hope the logic of this is clear. Then the detail, of course, I don't care too much. However, again, this diagram interferes with this other diagram where you interchange the two photons, again, because these are indistinguishable, okay? So the matrix element of this second diagram is very similar to the previous one, as we observed already for the Molar Scattering, except for the fact that the incoming and outgoing photon are attached to different vertices, okay? They're just crossed here. And this, in turn, of course, changes also the way the momentum flows into the virtual propagator. So in this case, we have P minus K prime instead of P plus K. So we can write down now the matrix element for this second diagram, which also contributes at first order. And you see that indeed now the photon wave function and also vertex factor are interchanged. Okay, and also in the propagator we have a plus sign here and a minus sign here. All the rest is just trivially obtained by applying the Famine rules. Now, of course, we want to make the sum of the two and take the average over the spin as usual, and you can write these easily in a compact way in terms of the Mandelstam variable, okay? Where S is now K plus P squared and U is K minus P prime squared. And finally, you put this into your cross-section, you further integrate over the solid angle, and you obtain your total cross-section as a function of S, so as a function of the square center of mass energy, which turns out to have these strange dependency in terms of the logarithm. The S also enters in the argument of the logarithm. So next one, I'm going quite fast because indeed I just want you to understand the principles, but not the details. I don't care about the details in these calculations. So this is now the E plus E minus into two photon annihilation process. Again, we have two contributing diagrams, okay? Again, the virtual particle is an electron. So again, we have to take into account this kind of electron propagator. So as we've done before, okay, we can calculate our squared spin average matrix element. We can express this in terms of the Mandelstam variable. The derivation, if you are very curious, you find in the Altscher-Martin textbook, one that I suggested at the beginning, quarks and leptons. It is quite, it's not straightforward, okay? So if you're really interested in algebra, you can go for these. I don't care about the passages, just I'm interested about showing you the final result, okay? Then, as usual, you can express your Mandelstam variable in terms of the theta angle. You can put this into our differential cross-section and can compare with, again, experimental data. In this case, we have experimental data from different experiments, from DESY, from SLAC, and from CERN, at different center of mass energies. You see from 14 GeV up to 92 GeV, okay? And so these are the prediction for the different value of S that enters here, okay? And you see that the results are in very, very good agreement with experimental data at all energies. Again, consider that these are only first order calculation. One can be even more precise by including the higher order terms. Now, the last thing I want to tell you today, let's get back again to the Compton scattering and this E plus E minus annihilation. Okay, so for the first case, I wrote you that this is the expression of the matrix element square in terms of the Mandelstam variable, and this is instead for the case of the photon, for the E plus E minus annihilation. Now, you immediately notice that the two diagrams are very similar. They're just rotated 90 degrees. But also the matrix elements are very similar. They are just obtained by exchanging T with minus S. Okay? And this is not just by chance. Okay? This is a consequence of the so-called crossing symmetry of Qed. So let's see what does this mean and how it helps also in calculating cross-sections. So let's go back to the distinction between S-channel and P-channel. Okay, so here we have two processes. The one is E plus E minus annihilation into a generic fermion-antifermion pair. And the second one is electron scattering with a generic fermion. Okay, so these are, of course, two different physics processes. Okay, but the topology, as you see, is very similar, okay? Each of them can indeed be approximately obtained by rotating the other by 90 degrees. And also, the currents which are involved, which enter at the end in the matrix element, can be obtained from the other by applying these very simple substitutions. Okay, so the first one is even the same, and then you just need to make this substitution in the current. Once you do so, you can immediately switch from the matrix element of one process to that of the other process. Or equivalently, this corresponds to make this change, this rotation into the Mandelstam variables, S to T, T to U, U to S. Once you do this, you can get the matrix element of one process by knowing the matrix element of the other process and vice versa. So this is indeed very useful. So the electromagnetic process was Famine diagrams are 90 degrees rotated, so are in S channel and T channel respectively, can be indeed coupled. And the topological similarity of their diagrams is reflected at the level of transition amplitude. And one can obtain the transition amplitude for one process by simply applying minimal substitution to that of the other process. And this is indeed the sense of exploiting this crossing symmetry. So let's consider these 6 processes, QED processes: Compton scattering, pair annihilation, Molar scattering, Baba scattering, Bremsstrahlung, pair creation. Based on the topology of their diagrams, we can couple these 2 by 2. So the Compton effect with the pair annihilation, as we did already, sorry, let me go back here, okay, as we already mentioned before, but also the Molar scattering with the Baba scattering and the Bremsstrahlung with the pair creation. Okay, and these slides summarize how to make use of this crossing symmetry to calculate your matrix element. So suppose we start from a Molar scattering, okay, where we do have, as we know, 2 contributing diagrams, okay, which interfere because they have the same fast-state particles. So indeed, when you look now at the squared average matrix element, we have 3 terms: the one for the first term, the one for the second diagram, sorry, and the one for the interference between the 2. Okay, let's now just make the change S with U. So let's just replace S with U. If you do so, you pass from this matrix element to this matrix element, which is indeed the one of the Baba scattering. Okay, so with a very simple, minimal change in your currents, by exploiting this crossing symmetry, you can get the matrix element of the other process. Here is another example. This is electron-muon scattering. So we have electron on top, muon on bottom, and we have a scattering, electromagnetic scattering mediated by the exchange of a virtual photon. This is the matrix element squared. Now you apply the crossing, you change S by T, and you get the matrix element of the E plus E minus annihilation. So the 2 are paired, etc. Okay? This is my last slide today, so we can stop here. Any questions? Ci siete, ragazzi? Battete un colpo.
Sì, sì, siamo.
E con i microfoni mutati ho l'impressione di parlare al muro. Okay. Allora, se non ci sono domande su questa parte di oggi, domani completeremo la parte di QED, quindi analizzeremo gli effetti di ordine superiore, l'effetto della coupling, della running coupling constant che ho accennato soltanto adesso. Quindi domani completeremo la parte di QED e cominceremo a introdurre poi la parte delle statistiche fermioni e bosoni. Ok? Vabbè. Se non ci sono domande o possiamo discutere, possiamo interrompere la registrazione intanto.